Now that we've had a chance to figure out how to get Maple to do our dirty work for us in terms of Euler's method, we're going to kind of go back and think about what the errors are in telling us about Euler's method. And specifically, we're going to take a look at the concavity of the situation in terms of the type of error that we expect. So, for example, if you remember back from Calc 1, learning about concavity, the value of the second derivative, if you're talking about something that's concave up, then f double prime is greater than 0. Right? That's kind of the textbook definition of what concave up means. Sometimes this is just referred to as concave, and this is referred to as convex, depending on where you learned or when you learned. But concave up and concave down are the two ways of thinking about concavity. So if f double prime is less than 0, we call that concave down. And just as a quick kind of visual representation of both of these, we're going to think about what each one of them means in a situation where we have some y versus t graph. And so if y is our function, then our second derivative is going to tell us what's going on. Because if we have a start and an end point here, so let's imagine that we're talking about some actual curve that has a starting point and is concave up, so it's going to curve like this. And so there's a start and end point, and that's the actual curve. Then our approximation using Euler's method is going to be a series of little dotted lines, little line segments that are going to always kind of tuck up, or kind of tuck towards going in the same direction, but it's never going to quite match because it's going to move out a little bit and then move out a little bit and then move out a little bit, and it's always kind of not quite curving nearly enough. And so our approximated curve, in this case, in the case of concave up, is always going to give us an estimate that is an underestimate. And that's just the nature of the beast when you have a concave up situation. But what happens with concave down? Well, kind of the opposite, as you might imagine. If you have a curve that's concave down, looks something like this, and that's your actual, then your approximated is always going to be, it's kind of just slightly underdoing it, right? It doesn't quite curve nearly as fast or as much as the actual curve. So our approximated curve in this case is always kind of underwhelming, but yet this is always going to be above the actual curve, and so we call that an overestimate. And so this is handy for us because what we can do is think about, we already know the first derivative because we have our differential equation. So in order to figure out the concavity, all we need to do is take a look at the second derivative. So on the top of the next page, if we checked into y double prime, and we take a look at y double prime in the vicinity of our starting point, we can know what kind of estimation error we can expect. So let's go back and use our former example. And just as a reminder, in our former example, we were talking about a function that looked like this, a differential equation that was y prime equals t squared minus y squared. And our initial condition was y of 0 equals 1. And so what I'm suggesting is we figure out what the second derivative is. Sorry about my microphone's falling over here. All we have to do is figure out what the second derivative is. So if I take the derivative of this entire equation with respect to t, then I'm taking the derivative of y prime. That's going to give me my second derivative. But now I have to take the derivative of this whole mess right here. And if you remember, taking the derivative of each one of these, we have to kind of take each term at a time. So the derivative of t squared with respect to t, that's just going to be 2t. The derivative of y with respect to t, using our implicit differentiation, is going to be negative 2y times dy dt. Now, just so happens that we already know what dy dt is. It's this thing right here, because that is y prime. So on our next line, all I have to do is write down y double prime is equal to 2t minus 2y times t squared minus y squared. And with a little bit of manipulation, you can see that this is now a function of t and y, but it's our second derivative. So what we're interested in is what's going on near the t value of 0 and the y value of 1. So off to the side, I'm going to say, so near t equals 0 and y equals 1, we can plug in those values and say y double prime is approximately equal to, I'm going to take this from down here, so it's going to be 2 times 0 minus 2 times 1 times the quantity, 0 squared minus 1 squared. And so with a little bit of effort, you can see that this is going to be y is approximately equal to negative 2 times a negative 1 gives me positive 2. And so that is definitely greater than 0. And that means our curve, y of t, will be concave up in this region. Right around t equals 0 and y equals 1, we expect it to be concave up, and that means that we expect our estimate or approximation to always be an underestimate. Right? And thanks to that previous page where we were looking at the relationship between concavity and the type of error we expect, we can know that going into it. So we can account for that, or at the very least expect it. So interestingly, it turns out that for basic Euler's method calculations and computations, there's a couple of nice relationships. That error turns out to be proportional to step size. So error and step size are directly related to each other, right? So as so as step size gets bigger and bigger and bigger, so does error, which is exactly what you expect. And as step size gets smaller, so does error. But remember, as the step size gets bigger, what happens to the number of steps that we have to take? It goes through the roof. So the other thing that we know, the relationship that we know, is computation time that is proportional to 1 over step size. In other words, as step size gets smaller, computation gets bigger. Right? So those two things are just kind of always true. Keep these in mind as you're using Euler's method on Maple to be able to do your calculations. Speaking of which, here's an opportunity to do just that. Here's another method. Another Euler's method example. This time, it's a chance for you to be able to try your chops out on doing this in Maple. So what I want you to do is take a second, let's read the problem, let's make sure we know what's going on, and then I'm going to give you a chance to fill in as much as you can of the table prior to using Maple, and then we'll have Maple do the heavy lifting for us, and then we'll go back and fill in some details later on. So right now, just hit pause, read the question, make sure you understand what it's asking. We're given an initial value problem in the form of a differential equation and an initial condition. So that's important to know, right? So there's our initial value problem collectively. The other piece of information that we're given is that t, the input variable, the independent variable, is going to go from 0 to 1. Now 0 happens to be the starting point. So this is telling us how far we have to go. So this is where the t value is going to end. So we can think of this as our starting t value. And this is our end t value. The question is, how many steps are we going to take? Well, the nice thing about this is if you know the step size and you know the total distance that you're going to travel, you can calculate that pretty easily. If a step size is 0.25 and you're going 1 unit, then you're going to take 4 steps to do that. So we're going to write this out down here in the table, and we're just going to start by filling in the first 2 columns. And the first 2 columns are really saying, okay, what number step are we on? And we're always going to start with the 0th step. So what is t with a little subscript 0? What is our initial t value? That's our start t value, that's 0. And while we're at it, we can fill in our y sub 0, our starting y value, and that is right here, 0.5. And for the rest of these 2 columns, it's actually pretty easy to fill in because after 1 step, your new t value is going to be where you were before, plus your step size of 0.25. So this is going to be 0.25. And after 2 steps, it's going to be another 0.25. And after 3 steps, it's going to be another 0.25. And after 4 steps, you're now at 1, or 1.0 if you want to call it 1.0. The question is, how do we fill in this column? And the answer is, we're going to let Maple do that for us. So take a second, hop on Maple, and make sure that you have figured out how to input the Euler's method using the proper code. I'll have the Maple notes included for this example for section 1.4, so you can take a look at those. But I'll let you hit the pause button here and fill that in. So the only other column that we can fill in from our Maple output is this right here. And this is our approximated y value, right? So this is the Euler's method approximation, right? And it turns out that this last pair of numbers right down here is actually the coordinates. That is our approximated endpoint. Right? So at the point 1 comma negative 0.8188, that's where we think our curve is going to get to. Now we know that it's not going to be there in actuality, but this is an approximation. These other 2 columns, Maple doesn't give to us, but we can calculate them. It doesn't take too much. This column, if you remember, this is really our slope at this point right here. So this column is saying, okay, here is the input and the output values, the t and the y values. What's the slope for those t and y values? And we get that by using our dE. This gives us our slope right there. And by the way, it also gives us that part of this equation right here. So all we have to do is quickly kind of throw some numbers into our equation and we can fill in that column. So I'm going to do that. I'll hit pause and do that so you can do that too. So those are the values for this column that I care about. Now you'll notice I didn't fill in the last cell in that column because we actually don't need to. We've already got our approximated endpoint, so we don't need to do any more of that calculation, or this one for that matter. Speaking of which, we have another column, and this column represents, if you remember, the step size times the slope. That's from our formula, right? And so if you were doing this all by hand, having this column would help us because we'd say that plus this gets you here. That plus this gets you here. And you could use, you could come up with this column and then do the calculation. You could program an Excel spreadsheet to do it if you wanted to. But remember, along the way, we're using our step size right there to do this calculation, a step size of 0.25 in order to do this calculation. So pause for a second. I'm going to pause for a second and then fill in this column. You do the same. Do the calculations. And like magic, it appears. So this column right here would help us find this column right here, right? Now Maple really only gives us these 3 columns along with the the Maple's numeric solution. It's highly accurate numeric solution so that we can compare Euler's method. But just keep in mind that these columns mean something here. This column gives the slope at the current location. Right? So the slope at t equals 0, y equals 0.5 is 0.25, right? So that's the whole purpose of that column right there. This other column, this guy right here, this tells us, this column gives the change in y coordinate for the next value, the next y value, right? So if you take your y value and you add this, you'll get here. If you take this y value and add this, which is subtraction, you wind up here. If you take that y value and add this, you get there, and so on and so forth. So this table really is set up so that we can kind of see the calculation. Now remember, Maple doesn't give you everything, but it gives you enough. And of course, you can have Maple do output on the table. Instead of giving you a table, you can have Maple do output plot to be able to create a graph like this. But with a little bit of effort, you can see what the curve might look like, what we approximate it to look like. Now, each one of these is a series of straight line segments, but these coordinates, this approximated endpoint that we found over here, corresponds to that point right there, right? So it's a way of being able to visualize what's going on, a way of being able to show where the calculations are coming from, but still making use of Maple to do kind of the heavy lifting for us. And of course, you could do these calculations in Maple as well if you wanted to. It's not that hard. So that gets us to the end of Euler's method. You're going to have plenty of opportunities to try this out, and you get some practice on the problem set as well as the classwork.